Good morning, dear student. In today's lecture, we will discuss the important topic of our course CHI 330 homogeneous catalysis, that is asymmetric catalysis. So, what is this asymmetric catalysis? Asymmetric catalysis is a type of catalysis in which chiral catalysts direct. So, it is a type of catalysis in which a chiral a chiral catalyst a chiral catalyst directs directs the formation of chiral compound, the formation of chiral compound. So what is this asymmetric catalysis? It is the type of catalysis in which a chiral catalyst directs the formation of chiral compound such that formation of formation of one particular formation of one particular stereoisomer is favor. Formation of a chiral compound such that the formation of one particular stereoisomer is favor. So this is the definition of asymmetric catalysis. It is a type of catalysis in which a chiral catalyst directs the formation of chiral compound such that the formation of one particular stereoisomer is favor. Again, if you see the design of this chiral catalyst, often start with a chiral metal complex. So whatever the design of chiral catalyst is often start with a chiral metal complex, a chiral metal complex that exhibit some activity in the desired catalytic reaction. So the design of chiral catalyst for asymmetric catalysis often start with a chiral metal complex that exhibits some activity in the desired catalytic reactions. Again, the important point is that one such a complex is identified one such a complex is identified, that is a chiral metal complex is identified, the ligands are modified in such a way that a chiral environment is created. So after identifying a chiral complex, then the ligands are modified in such a way that in such a way that in such a way that a chiral environment is created. So whatever the design of chiral catalyst start from a chiral metal complexes. So after getting a complex or after identifying the complex, the ligand is modified in such a way that a chiral environment is created. Further, the fine tuning of the ligand and other reaction condition fi- further the fine tuning of the ligand and other reaction condition may then undertaken to optimize the enantioselectivity selectivity of the reaction. So after all the conditions has been achieved, then it is undertaken to optimize the enantiomer selectivity of the reaction. Again, so at least you should remember this point, that is, the asymmetric catalysis is a type of catalysis in which a chiral catalyst directs the formation of chiral compound such that the formation of only one particular stereoisomer is favored. Design of chiral catalyst, it is start with a chiral metal complex. After the complex has been identified, then the ligands are modified in such a way that a chiral environment is created. Again, if you if you see this asymmetric catalysis, so whatever the ligands are used in this asymmetric catalysis are broadly classified into two types. So whatever the ligands, the next important point is that whatever the ligands used in this asymmetric catalysis, they are broadly classified into two type, that is, one is hard donor atom, hard donor atom such as nitrogen or oxygen. Hard donor atom, so this nitrogen, it is not a hard donor atom, it is a borderline, but for our convenient we consider this nitrogen, it is a hard donor atom. And the second, the chelating phosphine ligand, chelating phosphine ligand, chelating phosphine ligand. So you should remember, whatever the ligand, they are of two type. One is hard donor atom containing nitrogen and oxygen, and second is chelating phosphine ligand. If you consider the first one, the first type, if you consider the first type, so let us discuss the first type, that is hard donor ligand, hard donor ligand. And if you consider the important points regarding to these hard donor ligands, they are monodentate or chelating depending on the reaction. So these hard donor ligand containing nitrogen and oxygen, they are monodentate, monodentate or chelating, monodentate or chelating depending on the reaction. Again, the second important point is that the ligands can complex and stabilize the metal ion in high oxidation state. These ligands, can complex, this ligand can complex and stabilize metal ion in high oxidation state, in high oxidation state. Again, the important point is that these ligands with metal ion, these ligand with metal ion such as titanium in +4, then osmium is in +8, then rhodium is in +3, then manganese, it is in +3, etc. are used for reaction, such as epoxidation, second alkene dehydroxylation, and cyclopropionation, and cyclopropionation. So this is regarding to the hard donor ligand which is used in asymmetric catalysis. So these ligands may be monodentate or chelating depending on the reaction. This ligand can forms the complex with metal ion in high oxidation state. This ligand with metal ions such as titanium plus 4, rhodium plus 3, osmium plus 8, magnesium plus 3 are used for the reactions such as epoxidation, alkene dehydroxylation, and cyclopropionation. So, if we see the example of these ligands, so at least you should know the structure of this ligand. So, let's discuss these ligands. The first one, so we are very much familiar with this ligand, that is this is your binaphthol. Binaphthol. It is this is your binaphthol. If you consider this binaphthol, it is a chiral ligand. Binaphthol. It is a chiral ligand, and this chirality, whatever the chirality in this binaphthol ligand, chirality, it is due to the steric interaction, steric interaction in the molecule, in the molecule does not have a plane of symmetry. So the chirality is due to the steric interaction in the molecule does not have the plane of symmetry. So steric interaction in the molecule does not have plane of symmetry, plane of symmetry, and therefore it is chiral because both these ring are in different plane. So if you consider this is, you can write this as, so both these ring are in a different plane and therefore it is a chiral molecule or chiral ligands. Okay. If you consider this is the first complex, that is the hard donor atoms such as nitrogen or oxygen. So binaphthol. So chirality is due to the ring because both the rings are having in both the rings in different plane. Again, there is another example of this chiral ligand is your bidentate alkoxide, or double bond is there, or is there, OH is there, OH is there. So in this case whatever the R group is your ethyl or isopropyl group is there. Okay, it is bidentate alkoxide. We can consider this ligand, it is considered as a bidentate alkoxide. So whatever the ligand, binaphthol, and this second one, the name of this ligand is not given in the reference book, so at least you should know the structure of the ligand and try to find out the name of this ligand. So this is your bidentate alkoxide. So these are your bidentate alkoxide, bidentate alkoxide ligands. Again, one more is there. If you consider this lanthanum complex is there, oxygen is there. Again, the oxygen is there. In this there is a lithium. Okay, again here lithium is there, oxygen, and this is your oxygen is there. Again this is lithium is there. So this is whatever the structure we have seen, these are all bidentate alkoxide. These are the chiral ligands. So they are having a hard donor atom such as nitrogen and oxygen. So these two, whatever the complexes we see, it contain oxygen. Let us see one more example of this uh, chiral ligand which contain nitrogen. So this is the complex. This is your nitrogen is there. This is your pH. Again, it contain copper. So this is a complex. Again, nitrogen is there, double bond. Okay. So this is the complex. So this, whatever the metal complex and the ligand we see, these are considered as a hard or hard donor atoms such as nitrogen and oxygen. They will stabilize the metal ion in high oxidation state, and generally these metal ions, if you consider whatever the metal ion we study, they are used for epoxidation, alkene dehydroxylation, and cyclopropionation. Let us discuss the second important type of this chiral ligand is the chelating phosphine ligand. Chelating phosphine ligand. Chelating phosphine ligand. So we are very much familiar with this phosphine ligand. Uh, if you consider this ligand interact with metal ion which is present in low oxidation state such as rhodium plus 1, so they will interact with rhodium plus 1. Second, ruthenium plus 2. Then it will interact with iridium plus 1, and then nickel in zero oxidation state. So these chelated phosphine ligand interact with this metal ion. Again, they are used in hydrogenation. They are used in hydrogenation reaction. Then isomerization. They are used in hydrogenation, isomerization, hydrocyanation, hydrocyanation, and hydroformylation reaction. Hydroformylation reaction. So whatever the phosphine ligands, it will interact with this metal ion, and they are used in hydrogenation, isomerization, hydrocyanation, and hydroformylation reaction. So let's discuss the example of this phosphine ligand. The first one is PPH2. This is your PPH2. It is attached to this oxygen. Oxygen is there. So this is your first ligand. Again, the one more is there. It is very important. If we see the structure of this complex, it is a phosphine complex, chelated phosphine complex, which is attached to rhodium. This is your phosphine, and this is your again pH is there. It having OMe, and also having OMe residue is there, and it is attached. This rhodium atom, it is attached to these two phosphine, two phosphorus atom, and one more ligand is there, that is the norborane system is there. So we are very much familiar with this norborane system. So if you study in organic chemistry, this is your norborane system. If you consider, this is your double bond is there. Again, double bond is there, and it will interact, both this double bond, it will interact with this rhodium, and it having a positive charge on this complex. This is your rhodium complex, we are having two phosphorus and it is attached to the norborane ligand. This is the first asymmetric hydrogenation catalyst, you should remember. So whatever the complex we discuss, again we draw the structure. So whatever the complex, this is your rhodium is there. Both these carbon double bonds have having a bond with this rhodium. Again there is a phosphorus or phosphine. So this is your pH. Again this is also, we can write, this is also your pH is there, having pH is there, and they will interact in such a fashion. It's also pH having OMe, and this pH also having OMe is there. Okay, so this is a first asymmetric hydrogenation catalyst. First asymmetric hydrogenation catalyst. First asymmetric hydrogenation catalyst. If you consider, it is used for manufacturing of L-dopa. It is used for manufacturing of L-dopa, capital DOPA. So we are very much familiar with this L-dopa. What is the full form? You find out your own. L-dopa. So these are the some complexes. Also there is a lot of chiral complex, chelated phosphine complex is there, but we are not very much interested in these complexes. I will provide the structure and you have to find out the whatever the name of these chiral ligands. In the next lecture we are very much interested in the mechanism of this asymmetric hydrogenation with the help of this catalyst, rhodium catalyst. So this is all about the introduction regarding to the asymmetric catalysis. In next lecture we will discuss the mechanism of asymmetric hydrogenation using the rhodium complex. Okay, thank you.